What you're looking at isn't a star field. Every single dot of light in this image is an entire galaxy, billions of stars, trillions of planets, and there are 10 million of them captured in a single photograph, taken in just 10 hours. This is the first image from the Vera Rubin Observatory, and it's about to change everything we know about the universe. Most telescopes are built to stare deep into space, focusing on one tiny spot for days or weeks. Rubin does the opposite. It films the entire sky. Every few nights, it scans half the visible universe, hunting for anything that moves, explodes, or changes. And it just opened its eyes for the first time. The telescope sits on a mountaintop in Chile, nearly 9,000 feet above sea level. The air is thin. The sky is dark, and from this peak, Rubin can see farther and faster than almost anything humanity has ever built. At its heart is the largest digital camera ever created for astronomy, 3.2 billion pixels. That's not a typo. If you wanted to display one Rubin image at full resolution on regular 4K TVs, you'd need 400 of them, all running simultaneously, just to show one photo. But the camera is only part of the story. The telescope itself has a field of view 40 times wider than the full moon. In one exposure, it captures an area of sky so massive that Hubble would need months to photograph the same region piece by piece. Rubin does it in 30 seconds. And then it moves to the next patch of sky and shoots again, hundreds of times per night, building a living map of everything out there. Why build something like this? Because the universe isn't static, it's alive. Things are constantly changing. Stars explode, asteroids drift past Earth, galaxies collide. And for the first time, we'll be able to watch it all happen in real time. On June 23, 2025, the Rubin team released 3 images that stunned the astronomy world. The first was the Virgo cluster, a massive collection of galaxies 50 million light-years away. At first glance, it looks like someone spilled glitter across black paper, but zoom in and reality hits you like a freight train. Every speck isn't a star, it's a galaxy. Some are pristine spirals, arms stretched out gracefully. Others are torn apart, stretched into long streams of light by gravity. These are cosmic car crashes happening in slow motion across millions of years. You can see galaxies cannibalizing each other, bridges of stars connecting victims to their attackers, faint halos of gas that used to be entire civilizations of worlds, now scattered across the void. Hubble has photographed parts of Virgo before, beautiful close-ups of individual galaxies, but Rubin captures the whole thing, the forest instead of the trees. For the first time, we can see the structure of a galaxy cluster at this scale, with this kind of detail, the context, the connections, the violence. This isn't just a pretty picture, it's a map of dark matter. Every warped galaxy, every gravitational arc is a clue to where invisible matter is hiding. And Rubin will do this for the entire southern sky, mapping the scaffolding of reality itself. The second image hit differently. The Trifid and Lagoon nebulae, 2 enormous clouds of gas and dust inside our own Milky Way. This wasn't one photo, it was 678 individual exposures stacked together into what might be the most detailed wide-field image of this region ever captured. Red and pink hydrogen clouds glow like cosmic fire. Blue reflection nebulae shimmer where starlight bounces off dust. And cutting through everything are dark serpents of cold molecular gas blocking the light behind them. These are stellar nurseries, places where new stars are being born right now, and Rubin captured them with such insane dynamic range that you can see details that were invisible before. Faint outer halos, turbulent shock waves, cavities carved by newborn stars blasting their surroundings with radiation. You can zoom in endlessly, and the detail never stops. That's what 3.2 billion pixels gets you, a microscope for the sky that also happens to cover an area the size of several full moons. But the third result from those first test nights might be the most important.
Asteroids. In just a few nights of testing, before the telescope was even fully operational, Rubin detected thousands of asteroids. Some were known, but dozens were completely new. Small rocks a few hundred meters wide that had never been cataloged before, including several near-Earth objects, rocks that cross our planet's orbit. Here's why that matters. Most asteroid searches involve tediously comparing images taken hours or days apart, looking for dots that moved. It's slow, it's manual, and we miss things. Rubin automates all of it. Every night, it takes rapid sequences of the same patch of sky. Stars stay fixed, asteroids shift slightly. Software flags them instantly, and within 60 seconds, astronomers around the world get an alert. During one test session, an engineer noticed a faint dot behaving strangely. It was moving between frames, slow but steady. They ran the calculations. New asteroid, never seen before, added to the catalog. That's going to happen thousands of times, every single night. Over the next decade, Rubin is expected to find millions of asteroids, including tens of thousands of near-Earth objects we don't know about yet. It's planetary defense powered by machine learning and speed. But asteroids are just the beginning. Rubin is built to catch anything that changes. Exploding stars, colliding neutron stars, variable stars pulsing, quasars flickering, even gravitational wave events that produce visible light. The system works like this. Light hits the camera. Computers process it instantly. Algorithms compare it to previous images of the same spot. If something brightened, faded, or moved, an alert fires. Within a minute, observatories around the world can point their telescopes at the exact coordinates to follow up. It's like having a smoke detector for the universe, constantly monitoring, always watching, never blinking. And the data piles up fast. Every night Rubin observes, it generates tens of terabytes of information. Over 10 years, its archive will exceed half an exabyte. That's more data than most institutions produce in their entire existence. But here's the beautiful part. Much of it will be public. Students, amateur astronomers, researchers, anyone with an internet connection will be able to access the same database as professional scientists. You could discover a supernova from your bedroom. That's not hyperbole. That's the plan. So what exactly is Rubin going to do with all this power? 5 main goals drive the entire mission. First, dark energy and dark matter. By tracking how millions of galaxies are distributed and how their light is bent by gravity, Rubin will map the invisible scaffolding of the universe. It'll measure how dark energy has accelerated cosmic expansion over billions of years. Questions that have haunted physics for decades might finally get answers. Second, the solar system census. Every rock bigger than about 140 meters that crosses Earth's orbit will be cataloged. If something dangerous is headed our way, we'll know, with time to prepare. Third, the transient sky. Supernovae, kilonovae, fast radio bursts, gamma-ray bursts, things that flare up and vanish within hours or days. Before Rubin, we missed most of them. Now we'll catch them as they happen. Fourth, mapping the Milky Way. Rubin will track billions of stars, revealing faint stellar streams from galaxies our Milky Way consumed long ago. It's reconstructing the archaeological history of our own galaxy using light. And fifth, time itself. By imaging the same regions of sky 800 times over 10 years, Rubin creates a time-lapse of the universe. We'll watch galaxies evolve, stars die, black holes feed. For the first time, astronomy becomes cinema. The timeline is already set. In May 2026, the first major data release drops. Scientists worldwide will get access to reprocessed commissioning data to test their theories. By January 2027, the full survey begins. 6 months of data becomes public. And then the flood starts. Every few nights, the entire southern sky. Every patch revisited hundreds of times. Alerts firing constantly. Discoveries happening faster than papers can be written. There's something deeply poetic about all this.
The telescope is named after Vera Rubin, the astronomer who proved most of the universe is invisible. She studied galaxy rotation in the 1970s and found something impossible. Stars at the edges of galaxies were moving way too fast. The visible matter couldn't explain it. There had to be something else, something we couldn't see: dark matter. Her work changed everything. She proved that what we observe is just the surface. The universe has depths we're only beginning to map. And now, the observatory bearing her name is designed to find what we can't see by watching what we can, tracking how visible matter moves, how light bends, how galaxies warp, reading the invisible through its shadow. That first image, the one with 10 million galaxies, isn't just a photograph, it's a promise, a glimpse of what's coming, because that was taken during testing, a warm-up. The telescope wasn't even fully calibrated yet. Imagine what happens when it really gets started. Every night for the next decade, Rubin will be up on that mountain in Chile, scanning the southern sky, capturing billions of objects, watching for change. And every morning, the data flows to researchers around the world. The universe has always been dynamic. We just couldn't see it clearly enough. Stars have been exploding, asteroids drifting, galaxies colliding, all of it happening on timescales we couldn't track. Not anymore. For the first time in history, we're not just looking at the universe, we're watching it breathe, we're seeing it move, and we're recording every moment. The era of static astronomy is over. Welcome to the age of the living sky.